Hey guys, we are going to be talking about setting up rational equations. I know that this is going to be kind of challenging, so I wanted to start by giving you guys some general advice for how to set up these equations. We talked about it in class, but I'm going to default back to the good old triangle that you saw in physics. We all saw a triangle. It's probably on the wall in every physics teacher's room. That distance is a product of rate and time. And so people in physics classes have this little triangle thing, but really what this is telling me is that what this is really saying is that the rate is equal to what, distance over time? But we also get another arrangement of this formula. We can solve this equation for time as well, right? And time is going to equal, according to the triangle, distance over rate. All of the equations that you guys are going to get in the problem set is going to be some version of either a rate equation or a time equation. All right, this is the rational equations unit. So basically the variable that you're going to be solving for is either going to be a time or it's going to be a rate. So the idea is that if you are asked to, if this is going to be a problem where you're ultimately asked to solve find a rate, find a speed of the train, or find the rate at which somebody can paint a room or paint a fence or something like that. If you're going to need to solve for a rate, the unknown quantity is either going to be a rate or it's going to be a time. So if you're trying to solve for a rate, pick the equation where rate is in the denominator. So basically, if you're gonna be solving for a rate, then you're gonna want to set up your equation in terms of like adding or subtracting times together. On the other hand, if the unknown quantity is a time, if you're trying to find how long it takes for somebody to paint the room or how long it takes the train to get from point A to point B, if time is going to be the unknown quantity, that's a pretty good indication that you're going to want to use this equation over here because time is in the denominator. All right, this can get a little confusing though, because it's not always distance over time. Sure, you might have a problem that talks about like the speed of a car, and in that case, like the speed of a car absolutely will be something like miles per hour, right? A distance over a time. But the context can change. So it's not always going to be miles per hour. We might be talking about the speed of a bunch of people painting a room. So the speed of painting, it might not be miles per hour. It might be something like the number of rooms per day or something like that. Right? That's still a rate. It's still how quickly can somebody paint the room. So it might be rooms per day, or like this problem down here. My face is in the way, but we're talking about like we have inlet pipes that can fill a pool. So maybe it's maybe we're talking about the speed that a pool can be filled up, and maybe the rate then it's not going to be miles per hour or rooms per day. Maybe it's the number of pools per hour or something like that, or maybe it's the number of sinks that you can fill up per minute, right? The context can change, but those are all going to be rate problems. And and just to show you maybe the hardest ones to recognize, the hardest rates to recognize, at least for me, are when you have things that are averages. Averages are also rates. So like if I was going to talk about the average number of cookies that a classroom full of third graders eats, the average. How do you get the average number of cookies? You take the total number of cookies and you divide by the total number of children, right? That's also a rate, right? You can have an average that would be like, this classroom of children ate 3 cookies per child. All right, that's still a rate, but the units are a little bit weirder, right? It's not like miles per hour or rooms per day or pools per hour. It's the number of cookies per child, right? Or we might be talking about like buying something. We might want the average cost of a rose. And the average cost of a rose, that's also going to be a rate. Because how do you calculate that? Well, you take the number of dollars that you spend. It might be dollars per rose, or it might be number of dollars per dozen roses, or something like that. So the idea is that like averages can also be a rate problem. Now, the flip side of this, like we can do these exact same relationships, but do them in context, change the context around so that we're looking at the other variable. Right? So as an example, if you're not talking about a rate of speed, this same equation can be rewritten as a function of time. We could talk about like the time to get somewhere, time to get home or something like that from work, and time could be written as a distance over a rate. So it might be the number of miles divided by, I don't know, the number of how fast you're going, the rate. So maybe it's like miles per hour. And hopefully if you guys can notice when I divide miles by miles per hour, like the miles part cancels out. This is just equal to a number of hours, right? It's a time. This ratio is a time. And we can add times together if the problem calls for it. We're talking about the speed of filling a pool. Well, what if we needed the time to fill a pool? We can absolutely think about the time that it takes to fill a pool. We can think about that in terms of number of pools, total number of pools, divided by the speed at which you fill a pool. So it could be like the number of pools you can fill per hour. And again, dividing those two just turns into hours. It's just a time, right? You can do the same thing down here for, you can also take, we could also manipulate these equations. If you wanted to know the total number of children in a classroom, well, the total number of children in the classroom would be the total number of cookies that they ate, divided by the average number of cookies per kid. Divide those two things out and you get the number of kids. All right. Same thing for the average cost of a rose. If you wanted to know the total cost of all your roses, you can take the total amount of dollars that you've spent and divide by the average cost of a rose. All right. So being able to just like recognize that these are really just, this is all the same relationship, but sometimes the problem is going to be in terms of like a rate, and sometimes the problem is going to be in terms of the time. All right, so let's get into it. All right, guys, so here's the problem set. We're talking about question number 1, which is visible at the very bottom of the screen there. This says, if 2 inlet pipes can fill a pool in 1 hour and 30 minutes, and 1 pipe can fill the pool in 2 hours and 30 minutes, how long would it take the other pipe to fill the pool? Are you recognizing this as kind of like a painting the rooms kind of problem? Where basically we've got 2 different pipes. They're both filling a pool at different speeds. But we're going to talk about we're going to add the rates together and get the total, the rate of the total pool being filled up. So I like to think about it kind of like this. So we have 1 pipe, and we're going to talk about the rate at which it can fill the pool. We're going to be adding the rate which a second pipe can fill the pool. It's got its own rate of filling the pool. That's going to be related to our unknown. But if the 2 pipes are working together, then we have a total rate, right? It's like both of the pipes working together, right? We're adding the rates together to get some kind of total. So let's talk about what the rate is. All right, the rate is going to be in pools per hour. So what I'm going to do is I'm going to try and set up these rates as a number of pools per hour. This second pipe's rate is going to be a number of pools per hour. And when I add those 2 rates together, I'm going to get a total number of pools per hour. So let's start plugging in the numbers. If 2 inlet pipes can fill a pool in 1 hour and 30 minutes, right? If they're working together, they can fill 1 pool in an hour and 30 minutes, which I'm going to write as 1.5 hours. If 1 pool can fill the pool in 1 pipe can fill the pool in 2 hours and 30 minutes. So the rate for the first pipe is 1 pool in 2 hours and 30 minutes, so 2.5 hours. And we're trying to figure out how long would the other pipe take to fill the pool. So 1 pool in I don't know how many hours. That is that's the setup for this rational expression. I will leave you guys to do the to find the solution to that. Spoiler alert, the least common multiple of 2.5x and 1.5, the least common multiple, 7.5x is a good one to use. I don't know if that's really, it's a little bit weirder because we have decimals, but I was trying to think of like, trying to find a number that is divisible by 2.5x and 1.5. 7.5 is a nice clean number if you want to go with that one. All right, good luck. All right, here's problem number 2. If one inlet pipe, very similar to question number 1, if one inlet pipe can fill the pool in 2 hours with the outlet drain closed, and the same inlet pipe can fill the pool in 2.5 hours with the drain open, how long does it take the drain to empty the pool? Okay, so what we're talking about here, instead of adding rates together, we're really talking about the difference between 2 rates. All right, we have basically we have a pipe that's trying to fill up a pool, and it's either going to be like filling up the pool by itself, or it's going to be trying to fill up the pool with the drain open, right? So I don't know why you'd be trying to fill up a pool and keep the drain open, but apparently there's a difference there, right? Obviously, it's going to fill up the pool faster if the drain's closed. So what I'm going to how I'm going to think about this problem is I'm going to think about I'm going to have the rate at which the pool can fill with the drain closed. Like how quickly can the pipe fill the pool when the drain is closed? I've got another rate, which is how quickly the pool will fill when the drain is open. But there's going to be a difference in those speeds, right? The difference between like filling the pool with everything plugged up and filling the pool with the drain open, the difference in those is going to be your like the rate at which the drain can pull stuff out, right? The rate of the drain. So you can either think about this in terms of like the difference between these two, right? The difference in pool filling, the difference is going to be whatever the rate of the drain is. But you know, it's absolutely positively okay to also think about this as like, you know, you could think about this as like the rate of the rate of the pipe minus the rate of the drain. You could also think about it as like, I'm trying to fill up the pool with the pipe, but if the drain is open, is going to be subtracting something off of that rate, and that would get me my like total fill rate. You can absolutely set up the equation like that as well, but I think it's maybe a little more intuitive to talk about it in terms of like the difference between the 2 rates is how quickly the pool can drain. So we're talking about rates again, okay? So what are the units here? Just like in problem number 1, we're talking about pools per hour. All right, so when the drain is closed, we're going to be able to fill up the pool in some number of pools in some number of hours. Keeping the drain open means I'm going to be able to fill up some number of pools in a certain number of hours, but it's going to be a slower time. And then the difference in those 2 rates is going to be like the rate at which the pool could drain. And that'll also be in like pools per hour. So let's plug in the numbers. 1 inlet pipe can fill the pool in 2 hours. So 1 pool can get filled in 2 hours when the drain is closed. The same pipe can fill the pool in 2.5 hours with the drain open, right? So it takes longer if the drain is like working against you, right? But it could still fill that 1 pool in 2.5 hours if the drain is open. And we want to know how long does it take to drain the pool to empty if there's no water entering the pool. So basically 1 pool can get drained in how many hours? And that is one way to set up your rational expression. Get a common denominator, cancel it all out, see what you get for x. All right, let's talk about number 3. Number 3 is a little tricky because we're going to have some unit conversions to also deal with here. But we are talking about a car trip, and we're saying it takes 36 minutes less time to travel 120 miles by car at night than by day because the lack of traffic allows us to go 10 miles an hour faster than in the daytime. All right, so basically we can move faster at night because there's less traffic. Find the average speed in the daytime. All right, so before we actually set up the equation, let me just make it clear that look at what they're asking you to find. They're asking you to find the average speed. We're supposed to find a speed. That's our unknown, right? That's what we're going to be solving for. And if you remember in the triangle thingy from physics, speed is what? It's a distance over a time. So we're going to have to relate all these three things together, but the idea is that our unknown is going to be a speed. This is what we're ultimately going to be solving for. We're going to be trying to find a speed. So it is easiest then if you make your equation focused on times, adding and subtracting times together, right? The other quantity. And as we know, so this is going to be easiest to make the problem about time. So specifically time, the time in the daytime, the time in the nighttime, how long it takes to travel those 120 miles. For both cases, for during the daytime and the nighttime, we're just going to take some kind of distance and divide by speed. That puts our unknown quantity in the denominator, and that's what the whole point is, right? We're solving rational equations, so the unknown quantity is going to be in the denominator, right? So this kind of helps you kind of orient yourself around the problem, all right? So I'm going to try and think about adding or subtracting times. It's probably easy. To me, my brain makes it, I feel like we can take the time during the day, like how long it takes to travel during that 120 miles during the day. I like to think about the difference between the time during the day and the time at night. And because they're telling us, right? I mean, in the problem, maybe I didn't have to do all this stuff. Maybe it was clear that this is a problem ultimately about time. It takes 36 minutes less time to travel 120 miles. It takes 36 minutes less time. The difference in these two times needs to be 36 minutes. All right? Well, and here's our unit. Be really careful here because it's particularly frustrating that they gave us 36 minutes there. The speeds are in miles per hour, so don't put 36 here. Let's just go ahead and change these 36 minutes. Let's just change them into hours and call it 36 60ths of an hour. What is 36 60ths of an hour? That's 0.6 hours. All right, so careful there. Exclamation points. I'll put some exclamation points there. It's not just 36 minutes. Change it make the units match up. So we want to change that into hours. All right. So the idea is what we're talking about the difference between our time, how long it takes to drive somewhere during the day, and how long it takes, the time it takes to drive that same distance at night. The difference in those two times is 0.6 hours. All right. So let's now just talk about how to subtract those two times. What is time? It's distance over speed. So what I'm going to do is I'm going to have a distance over speed in the daytime, and I'm going to have a distance and a speed at night. And the idea is the difference in those two times. And I know it's weird talking about time as a fraction of distance over speed, but the difference in those two times needs to be 0.6. So now we can start plugging in numbers. We already have the 36 minutes taken care of. What is the distance that we're traveling during the day? It says we're traveling 120 miles. I guess at night we're also traveling 120 miles, so I can go ahead and slap 120 into both of those. But what's the speed? The speed is the unknown quantity. Find the average speed in the daytime. So I don't know how fast we're going. I don't know how many miles per hour we're going in the daytime. So I'm just going to leave that as x. The important part is that at nighttime, how fast are we going? average speed is 10 miles an hour faster than in the daytime. So if I can go X miles an hour during the daytime, I can do 10 miles per hour more than that at the nighttime. And so that takes us to our rational expression. 120 miles over some speed minus 120 miles over that speed plus 10. Somehow that's got to equal 0.6. Figure out the speed in the daytime. All right, here goes number 4. The difference in average speed for two trains is 16 miles an hour. The slower train takes 2 hours longer to travel 170 miles than the faster train takes to travel 150 miles. Find the speed of the slower train. Okay, so we've got two different trains. One goes fast, one of them's faster, one of them's slower. All right, and they're asking us to find a speed. All right, so just like what we were talking about earlier, if they're asking us to, just like in problem number 3, if we're asked to find a speed, speed is going to be in the denominator of these rational expressions. So in our little triangle of speed equaling distance over time, I'm going to be trying to find a speed. Speed is the unknown quantity. So that's telling me, that's giving me a hint that I should make my equation about time. Specifically the time for the two trains, right? We got a fast train and a slow train, but however long it takes them to travel their respective distances, we're going to try and write these time values as some distance over speed, right? I'm trying to find speed, so I'm going to try and write my equation in terms of the other variable, in terms of the time variable. That's going to make this the easiest on you. It's probably worth noting that you can absolutely set this up as a difference between two speeds instead of the difference between two times, but it's just like there's just extra steps in it. You'd still come up with the same answer though. So if that's how your brain is organizing this information, there's nothing wrong with that. But I'm going to try and do it in terms of a time equation, because what do they tell? They tell us that there's a difference they tell us what the difference in time is. The slower train takes 2 hours longer to travel 170 miles, right? So, so basically I'm talking about, I have a fast and I have a slow train. So the difference in time, the slow train time, because he's slower, that time's going to be more. So the difference between the slow train time and the fast train time, the time it takes to go 150 or 170 miles, the difference in those times is going to equal, they say the difference is 2 hours. Right? The slower train takes 2 hours longer, right? So the slower train is 2 hours longer than the time it takes the fast train to go. So how do we set up our time equations? Well, time, as you know, right, as we talked about up here, it's some distance divided by some speed. So I'm going to do another some distance divided by some speed. And when I subtract those two expressions, those two time values, the answer needs to be 2 hours. All right, so what about our slow train? It says we're trying to find the speed of the slower train. Okay, so I don't know what the speed is, but the slow train, it says the slow train takes 2 hours longer to travel. How long? 170 miles at whatever rate it's traveling. I don't know yet. It takes 2 hours longer for the slow train to go 170 miles than it takes the faster train to travel 150 miles. And how fast? What's our expression for how fast the second train is going? The fast train. It's going 16 miles an hour faster. So how about I write x plus 16? All right. So you're trying to keep track of where all these variables are going. We have a distance over an unknown speed, and then we have a second distance over a speed that's 16 miles an hour faster. But the difference between those two times is going to be 2 hours. So there's your rational expression. See if you can solve for x. All right, guys, problem number 5. This is a slightly different context than what we've been talking about, but we have been talking about rates and averages. In this case, it's going to be the average price. That's also going to be a rate. So a school library spends $80 a month on magazines. The average price in January is 70 cents more than the average price in December. Okay, so there's a price increase. Because of the price increase, the school is forced to subscribe to 7 fewer magazines. How many magazines did the school library subscribe to in December? Okay, so we've got December and we've got January, and we're talking about the average price. Now, I know you guys are used to, so far the problems that we've been talking about have been speeds, and the rates we've been defining as distance over time, and we've been trying to make equations where we're adding rates together. Well, in this problem, we're talking about the average price of a magazine. Well, that's a rate, but it's not distance over time. It's the total amount of money that you spend divided by the total number of magazines. So it's still a ratio, but instead of like adding these kind of ratios, we're just going to add those kind of ratios. And what's going on is we have there's basically a price increase. So we have the average price in January, and they're telling us that the difference in price between January and the average price in December, they're telling us that the difference was 70 cents, right? It was 70 cents more in January than in December. So the difference in these two average prices needs to be 70 cents. Okay, so I'm gonna subtract two averages. But what are the averages made up of? Well, it's the amount of money divided by the total number of magazines, right? So my average price in January, I'm gonna think about that as some money, some amount of dollars. Well, let me just use the word dollars. Dollars over the total number of magazines. That's going to give me my average price. In December, before the price increase, I also am going to have that average listed as some kind of dollars over number of magazines. And again, the difference in those two averages needs to be 70 cents because there was a 70 cents increase. So now let's start plugging in numbers. A school library spends $80 a month on magazines. It sounds like it's that amount of dollars in both months, right? So we're talking about $80, but we're dividing by a different number of magazines, right? So we need to find out how many magazines did the school library subscribe to in December. So we want this to be X. So let's see, what is the other number of magazines? Because of the price increase, the school library was forced to subscribe to 7 fewer magazines in January. So however many magazines we were buying in December, we have 7 fewer magazines in January. So there's my rational expression, my rational equation. See if you can find out what X is. All right, guys, here goes number 6. We are talking about an investor who buys a number of shares of stock for $1,600, but then unfortunately the price drops by $10 per share. And then the investor decides to sell all 4 shares of the stock for a different price. So how many shares did she buy originally? Okay, so this is going to be very similar to problem number 5, in that we're comparing a ratio, but it's sort of in disguise because we're talking about the cost per share. So like, how much does 1 share of this stock cost? The cost per share is a ratio. In fact, that cost per share, how do you calculate the cost per share? Well, you take like the total number of dollars that you spend and you divide by the number of shares that you own. All right, and we're going to be trying to figure out, right, how many shares did she originally buy? We're going to be trying to figure out, the unknown is going to be the number of shares that she originally bought. So that's going to be in the denominator of this fraction. Okay, so what's happening to the cost per share? Okay, well, she's got a buy cost per share. but then the cost per share, it goes down by $10, and then she's at some kind of new, it's going to be some new cost per share, and that's when she decides to sell it all off. And there's also going to be like a cost per share to sell. So the idea is like she's going to buy something at a certain cost per share, then the price goes down by $10 per share, and then she's going to sell it off. So how are we writing these ratios? What is the cost per share? Well, the cost per share, it's the dollars over shares, the number of shares. So I'm going to take some number of dollars per share when she's buying the stock. I'm going to subtract $10, and that's going to leave me with a different amount of dollars per share. All right, so let's throw in the numbers here. What are we talking about? We've got, she buys a number of shares of stock for $1,600. Okay, so she spent $1,600 on a certain number of shares, but we don't know how much that is. That's what we're going to try and figure out. But after that ratio drops by $10, then she's selling off all but 4 of her shares. So she sells off all but 4 of her shares for $1,120. So I can put $1,120. But how many shares? How many shares go in the bottom? What did that $1,120 buy? It's all but 4 of her shares. So however many shares she used to have, she sold all but 4. She still has 4 left, right? So now that should be your rational expression. Try and solve it for x. All right, for number 7, there isn't any equation that we need to set up. We're actually just given Newton's law of universal gravitation. And we just need to try and figure out what that equation would look like if we solved it for g. So right now the equation is in terms of F, which I believe is what the force between two objects. And apparently that is the gravitational constant, g, times the mass of the first thing, mass of the second thing, and then r squared. So that's like the distance between the centers of mass squared. So what we want to try and do is we want to try and get this equation solved for g. Like, what is the gravitational constant? You may even remember what it's supposed to be from your physics class. So how do I get that? How do I isolate the g? G's in the numerator, which is good because that means I could just multiply both sides through by this denominator. So step 1 would be multiply both sides by r squared. So I would end up with f times r squared on the left. And on the right-hand side, I would just have the numerator, gravitational constant times mass 1 and mass 2. Again, I'm trying to get g by itself. So I now have g being multiplied by mass 1 and mass 2. All you need to do is just divide both sides of the equation by those two masses. All right, so divide this by mass 1 and mass 2. Divide the left-hand side by mass 1 and mass 2. What ends up shaking out of that is you have a fraction on the left. You've got the force, the distance between them squared, between the two objects squared, divided by mass 1 times mass 2. And that should be a formula for the gravitational constant that you all learned in physics. All right, question number 8, we're back into equations. So, equations where we're adding, looks like rates this time. Huck Finn can paint a fence in 5 hours. Tom Sawyer can, if Tom Sawyer helps him paint the fence, they're obviously going to do it faster, so they can do it in 3 hours. How long would it take Tom to paint the fence by himself? Okay, so this is just like the example that we worked through in class the other day where we're painting the rooms, only this time it's 2 people and they're painting the fence. So the idea is that we can add their rates together. So we have Huck's rate, and basically if we add on Tom's rate, then we get some kind of like total rate of painting a fence. So what is the rate? What are we talking about with the rate? By rate, Good old physics triangle thing. The rate is going to be the number of fences that they can paint and the time looks like it's in hours. All right, so the rate of fence painting is going to be in terms of fences per hour. So Huck's rate is going to be a certain number of fences in a certain number of hours. Tom is also going to be able to paint a certain number of fences in a certain number of hours. And when we add them together, we will end up with an overall rate that is also going to be fences per hour. So let's plug in all the numbers here. We've got Huck Finn can paint one fence in 5 hours. So one fence, 5 hours. If Tom Sawyer helps him, all right, so if they're working together, they can do one fence in 3 hours. So if they're working together, one fence in 3 hours. And we want to know what would how long would it take for Tom to paint the fence by himself? So I don't know how many hours it would take him to paint the one fence, but that's what the question is asking. So 1/5 plus 1 over x equals 1/3. Figure out what the value of x is. All right, question number 9. We are considering a rational equation, 1 over r equals 1 over x plus 1 over y, and we are supposed to find the value of r when x is equal to 2/5 and y is equal to 3/4. Okay, so we have 1 over r. It's got to equal 1 over x plus 1 over y, and we're trying to figure out what does this look like what is r when x is equal to 2/5. So 1 over 2/5, and y is equal to 3/4. So 1 over 3/4. What is the value of r? All right, so when I think about trying to solve this equation, I'm noticing immediately that 1 over 2/5, 1 divided by, I can just write the reciprocal of 2/5. So 1 over 2/5 is just 5 over 2. Just turn the fraction upside down. 1 over 3/4 is just turn the fraction upside down, 4/3. And apparently when you add those two together, you get 1 over r. So let's add those two expressions together. 5/2 plus 4/3. Let's see. Do we want to do this? Do you want to try and get a common denominator? Maybe we should do it that way. Let's do it that way. Let's get a common denominator since it's a rational expression with the variable in the bottom. Least common multiple of r, 2, and 3. Least common multiple appears to be 6 and an r. So I'm going to basically try and get every single denominator to have a 6r in it. So multiply top and bottom by 6. This second fraction, it's over 2, so I'm going to need a 3 and an r multiplied into the top and bottom of that guy. And then 3 in the denominator means I'm going to need a 2 and an r multiplied into the top and bottom of it. Once you have 6r in every single denominator, right? 6r, 2 times 3, 6r, 3 times 2, 6r. Once I have 6r in every single denominator, then I can just multiply through by that common denominator, and I'm left with looking at the top, the numerators. So 6 times 1, I'm really trying to figure out how do I make 6 times 1, how do I make 6 equal 5 times 3r? How do I make 6 equal 15r plus 4 times 2r is 8r. How do I make 6 equal 15r plus 8r? Well, that's a total of 23r. And so when you divide 6 by 23, I'll just leave it as 6 over 23. R is whatever 6 over 23 is. That is the value of, I guess it's capital R. That's the value of r that would make that equation true. That was part A. They're asking us to do something else with this too. Solve the equation, solve this original equation, solve that guy for r. So let's do that too. If I have 1 over r equals 1 over x plus 1 over y, how would I solve that equation for r? Since the variable's in the denominator, we're basically going to do a similar kind of thing. We're going to get a common denominator and multiply through by that common denominator. So what's the least common multiple of all those denominators? I've got an r, I've got an x, and I've got a y. R, x, and y are all again multiplied together. That is the least common multiple. So this guy already has the r. I'm going to multiply an xy into the top and bottom of him. This next fraction, 1 over x, it's got x in the denominator. It needs the r and the y part. 1 over y, y is in the denominator, so it's going to need an x and it's going to need an r. So it needs the x and it needs the r. So now I've got this. Now I've got a common denominator. Is it clear that in each one of these fractions I have an r, an x, and a y? Rx and y, Rx and y, Rx and y. If the denominators are all the same, you can multiply through in one step, multiply everything through by Rx and y, and it just leaves you, all those fractions cancel out, and you're just left with the numerators. What are the numerators? Well, xy has to equal ry plus rx. And remember that we're trying to solve this equation for r. So I need to get these r's to appear in the same place. You can do that by just factoring out. Now that you have like r on the same side of the equation, you can just factor an r out of both of those terms. All right, factor an r out, so there's only one copy of it now. And then how do I get r by itself? Just divide both sides by that by that quantity in parentheses. So I'm going to divide both sides by y plus x. So I think I'll have xy on top, but I'll have y plus x on bottom, and that is my expression for r. That's the general formula for how to come up with the value of r given any x's and y's. We can actually test that by plugging in 2/5 and 3/4 and verifying that when you plug in 2/5 and 3/4 into this equation, you end up getting the expected 6/23. All right, last problem that is not an extension problem. All right, we have an ecosystem of rabbits, and it's apparently the population of rabbits is modeled by this weird looking equation, which is like 60 over 1 plus another fraction, 5 over t plus 1. T is time in years, and P is the population. So apparently you can plug in any time you want, and it'll give you an estimate of the population. So what are we asked to do with this? What is the rabbit population in year 10? All right, so all we have to do is just plug 10 into that expression and see what it shakes out to be. So 60 over 1 plus 5 over 10 plus 1. So that's really 60 over 1 plus 5 over 11. So because they're not asking us to do anything too special with this, you can just go right on over and plug in 60 over 1 plus 5/11 into your calculator, and that will tell you the answer is 41.25. Of course, we can do that algebraically as well. Since this is all about like simplifying expressions, maybe we should talk about how do you take 60 over 1 plus 5/11 and turn it into 41.25. This is math you guys can handle. If I'm looking at this denominator, 1 plus 5/11, I can add those two numbers together. Think about 1 as 11/11. So if you take 11 11ths and add 5 more 11ths, that means you'd be talking about 11 plus 5 is 16 11ths. So we're talking about 60 over 16 11ths. Unless you really love dividing by fractions, I'm going to choose to rewrite that as a multiplication problem. Instead of 60 divided by 16 11ths, I'm going to write that as 60 times its reciprocal. So 60 times that fraction upside down, 11/16. And then, let's see, does anything cancel? I guess there's like 4 as a factor. So pull a 4 out of the top, and 65 by 4, 15. All right, so this doesn't get like super clean looking, but 15 times 11, that's like 165, and 4 is on the bottom. And what do you want to bet that 165/4 is? 41.25. Let's see. 165 over 4. Perfect. All right, the next part of this question is going to ask you to solve that equation for t, but that is an extension problem, so we're not going to talk about it in this video clip. All right, this is the algebraic walkthrough of all 10 problems to take you to the actual solutions. In the first problem, I'm looking at those denominators and looking for a least common multiple. Turns out 7.5 is a nice clean number that can divide evenly by all three of those denominators. So, I'm going to try and work on getting 7.5x into each one of the denominators. So I'm multiplying in by what's missing. Now that all three denominators have 7.5 x's in them, I can multiply through and just focus on making the numerators match up. So negative 3x plus 7.5 has to equal 5x. A little bit of algebra tells me that x is equal to 3.75. Done. Question number 2. This was also a pool problem, but this time we had the drain working against us, and so the idea was that the pipe can fill up one pool in 2 hours. The drain, when the drain is open, the one pool can fill up in 2.5 hours. I'm looking at those denominators, and it looks like the least common multiple of 2 and 2.5 and x is 10x. So step 1 is to maybe get all of your denominators looking like it has a 10 and an x in it. 10x, 10x, 10x. All three denominators have 10x. So I'm going to multiply through by that denominator, and now I'm looking at the numerators. 5x minus 4x equals 10. That means x is equal to 10. Perfect. Question number 3. We had to be careful with units, remember, on this one. We had 120 miles at x miles an hour, and then we had something else that was going 120 miles at x plus 10 miles an hour, right? Because we were traveling faster. And we were apparently supposed to, the difference is 36 minutes, so make sure you're dividing that by 60 to turn that into hours. So then you're going to be looking at the denominators x plus 10, and 60, and finding a least common multiple. So I'm going to get every single denominator to have an x, a 60, and an x plus 10 in it. So that takes a minute. And don't get scared, these values are going to get a little big, but each denominator now has a 60x and an x plus 10 in it. So now I just need to deal with the numerators. So I'm going to multiply all of this stuff together. I've got 60x plus 60. I'm still going to have to multiply that by 120. I've got a minus 120x that's going to need to multiply by 60. And on the right-hand side, I've got 36x that needs to multiply by x plus 10. So another round of distributive property. These numbers are getting kind of large. Don't panic though. You'll see in a second that it looks like, see how there's 7,200 x's and then a minus 7,200 x's? Those can just cancel out. But it is a quadratic, so I'm going to move everything over into one side of the equation. It's got a leading coefficient of 36, so I'm going to go ahead and factor out that 36. That'll leave me with x squared plus 10x minus 2,000. You're still having to deal with what numbers multiply to get negative 2,000, but add to get 10. Those numbers are positive 50 and negative 40. You could also throw that into the quadratic formula at that point if you didn't feel like thinking about the factors. But out of negative 50 and positive 40 as your solutions, negative 50 doesn't make sense, so I kick that one out. The only solution is positive 40. All right, and number 4. Let's see, this is, we had 170 over x minus 150 over x plus 16, and the answer is supposed to be 2. Like the difference between those two rates is just 2. So we are going to get a least common multiple of x times x plus 16. So do a little bit of work to make sure all those denominators are the same. They are. And then focus on the numerators. So I'm going to have to do some distributing here to get rid of the parentheses. It looks like, I don't know what 170 times 16 is. Hold on. All right, 2720 minus 150x. All right, so now everything's distributed. It's still a quadratic, So I'm going to need to get everything onto one side of the equation and try and factor it. So let's see, so 2x squared, I'm going to need to take away, what are those x terms? All right, 2x squared minus 12x minus 2720. I can factor a 2 out of everything. That will leave me with x squared minus 6x minus 1360, and you're still left with trying to figure out numbers that multiply together to get negative 1360 but add to get negative 6. Those numbers happen to be negative 40 and 34, but again, at this point, if you don't like thinking about factors of negative 1360, just throw it into the quadratic formula, and it'll spit back the exact algebraic solutions. Since the factors are x minus 40 and x plus 34, that means my solutions would be 40 and negative 34, but negative 34 again doesn't make sense in the context of the problem, so 40 is our only solution. Number 5. We are taking 80 over x, and we had to add 0.7, and the answer is supposed to be 80 over x minus 7. So look at those denominators, try and find the least common one. It looks like I'm going to need an x and an x minus 7 in every denominator. So let's work to get those denominators the same. Perfect. Now we can multiply through by that common denominator, and I'm only left with figuring out the numerator stuff. That 0.7 might be a little pesky here in a minute, but we'll be able to handle that. If I go and distribute all those terms, distribute the 80, and distribute the 0.7x, let's see. Oh, well actually, okay, I'm noticing that I've got 80 x's on both sides of the equation. That's kind of nice, because then I can just take away an 80x from both sides. They just go away. And my quadratic should be 0.7x squared minus 4.9 minus 560. But y'all, I don't like dealing with the decimals, so I'm just going to multiply both sides of the equation by 10 to like kill that decimal. I don't like decimals. So multiplying everything by 10, you end up with 7x squared minus 49x minus 5600. I can factor a 7 out of all of those terms, and then you're left with trying to figure out what numbers multiply to get negative 800 but add to get negative 7. Those numbers happen to be negative 32 and positive 25. So my two solutions would be positive 32 or negative 25. But again, negative 25 doesn't make sense, so we stick with the 32. Question number 6. We have 1600 over x minus 10. This is the one about the stock. And then 11, it's supposed to equal the difference. It's supposed to be 1120 over x minus 4. So we look at those denominators and we say, okay, well, I'm going to need an x and an x minus 4 in each denominator. So I'm going to work on getting that common denominator. Now they all match up. Perfect. So multiply through by the least common multiple. And we're left with, I distribute this 1600 into those parentheses. Okay, the numbers are getting big again. And we're left with a quadratic. All right, so okay, so let's move all the quadratic terms over to one side of the equation. Looks like I have 10x squared, but how many x's would I have? It looks like I have 1120 on one side, but I'm going to be taking away 1600, taking away 40. Perfect. Negative 520 x's. And then I'm just going to move that negative 6400 over to the other side. So now it's a quadratic. It looks like 10 is a common factor, so I can at least rip that out, make the problem a little more manageable. X squared minus 52 plus 640. That factors to x minus 32 and x minus 20, so my two solutions are 32 and 20. Interestingly enough, these are both acceptable solutions to this problem. I didn't have to kick either one of those solutions out. There's two solutions. Number 7 was done in an earlier video, so I'm not going to repeat that. Number 8. This is the Tom Sawyer problem. So Huck can paint one fence in 5 hours. Tom can paint one fence in I don't know how many hours, but working together they can paint one fence in 3 hours. Least common multiple looks like it's 15x. So I'm going to work to get 15x into every denominator. Then I multiply through, and I'm just left with those numerators, and oops, sorry, I'm running off the page here. The should be 5 hours, should be how long Huck Finn should take. All right, and then numbers 9 and 10 were also done in an earlier video.